Now today life is unthinkable without electricity. So large-scale generation and the use of electricity is just over 100 years old. So electricity is a form of energy which we got very used to, and it's easily obtainable by conversion from other energy forms. And it's also easy to move this electrical energy from place to place efficiently with very little loss of energy, and it can then easily be converted to other forms for use. One example is your electrical motor. So looking at the history, the first power systems were installed in early 1880s, which was then a DC system, and that was the Edison's Pearl Street plant in New York. Then we had single-phase AC systems in the 1890s. Okay, we have Troy as well. Welcome, Troy. So we now at least 3 people all together. Then we have the free AC power that followed a few years later. And then we have large-scale distribution. Yes, hello to you as well, Troy. Welcome. We just started with the webcast, and we are looking at the historical overview. And on this side, it's Ricky Marks that will present this module for you. Now, major steps in electricity production. We have power generation, which converts other forms of energy into our electrical energy. Then we have the transmission part that conveys this electrical power to the major load centers. Then we have power distribution, which now distributes that electricity to all the consumers. So that's how we broadly can divide the electricity production into. Now, looking at the power system itself, power generation plants are located close to places where there's lots of fuel that it will use available. Other considerations is things like water as well as pollution. So you'll find them often in remote locations. And the loads are then situated in population areas. So we need to transport this generated power to the population centers where the people want to use the power. Now, almost the entire power generation and transmission is by AC, alternating current. Why AC? Because it lends itself to voltage changes easily, and we do that with our transformers. And voltage can be chosen for optimum efficiency and optimum capital cost. So we have better economy of power system operations. Now, later on, we'll talk about AC/DC, but once we go beyond 800 kilometers, then you'll see we start looking at DC systems in terms of transporting that energy. So up to 800 kilometers, that's the break-even point between AC and DC transmission. Okay, we are steadily growing. We have Dwayne as well joining us now. So maybe by past, we might have 10 people. Now, we have an AC waveform. So voltage or current in our AC circuits varies cyclically with a number of times per second. Now, this number is called the frequency. And the time for one cycle is 1 over the frequency. And this variation follows the sine relationship, and that's why it's called the sine wave. And electrical systems can be single or three phase, although we would normally work with three phase. Here's an example of a single phase generator. So there is one cycle of the sine wave, and if it's 50 Hertz, it means it will be 50 cycles per second. So we'll have 50 of these cycles within 1 second, which means the time for one cycle is then 1 over the frequency, which gives us 20 milliseconds. So that T is equal to 20 milliseconds. And this is no example of a single phase generator. So they design the windings in this generator so that it generates the sine wave at the end of the day. Now, we have vectors and phasor diagrams, which is applicable to sinusoidal AC waveforms. So we start with 0. So there is the direction of rotation of this vector. And then you can see we increase, we go to 50, 60, 90 degrees, which is where we have the maximum, first maximum, and then down to 180 where we have the 0 again in this waveform before it starts to go negative. So that's just to introduce phases. Now for free phase, we have 120 degrees displacement between the free phases. And I've tried to indicate the colors as we know them, red, black and blue for the different phases. So it's a free phase generator, so you see immediately we have 3 windings as well to generate the 3 different phases in this free phase generator. So that 120 degrees, so that's if the one is maximum at 0, the other one will be maximum at 120 degrees. So we've got 120 degrees displacement between the 3 different phases. Now, free phases is universally adopted because of lower equipment cost per unit power handled, and it's helpful if you interconnecting several generating sources. So the sources tend to remain in phase and stay synchronized. Free phase AC motors, which account for most of the energy that we use today, it's got a simple design and are self-starting. Now we will have a bit of a refresher on electrical power calculations. Now in a DC circuit, power is equal to voltage times current, and energy is power times time. So that gives us watt hours, and power we express in watts. Now in the AC circuit, the instantaneous voltage and current keep changing. Why? Because they are following this sinusoidal waveform. Power is then computed in root mean square, RMS voltage and RMS current. Now, if we want to know, if we have a circuit, let's say it's a DC circuit, and we've got some sort of resistor element, and we want to know what's the heating effect if we change this DC source, like in this example over here, now to an AC source. So if we want to compare that heating effect, then we must take the RMS value of the AC waveform. So that's why we have an RMS value. So that gives us, that RMS value must be 240 if we want to have exactly the same heating effect that we have with 240 volt DC. So that's why we have the RMS value. We also have an average value for the AC waveform, which is lower and which is different. But we use the RMS value because that will give us the same heating effect if we take a simple circuit. So the instantaneous power will then be the voltage and the current at one specific time. So if, let's say, the dotted line is the current and the solid line the voltage, so at that specific point in time, PT, that will give me the power. So the sinusoidal voltage and current are then defined in RMS magnitudes. So we want to know what is that value, which is equivalent to the DC value, and that's given by the RMS value. And that's equal to the peak divided by the square root of 2. So there's the peak value. Okay, the peak value of this waveform. And then similar to the current, because the current is also a sinusoidal waveform. So here you can see on one graph, you can see the voltage V in red and the current as well as the power. So you can see for a single phase circuit, what we now have is the power is oscillating. Okay, so it's not a nice way if you want to convey a lot of power. So that's why the free phase is advantage, and that's why we would normally use free phase. Now this you'll see if you do your practical. In your practical with this you can change the phase between the circuits. So there's now zero, they are in phase, the current and the voltage. And you have a slider that you can move around, and that as you move it around it will give you the value of the voltage, the current and the power as well. So again you can see power going to zero. So it's an oscillating power waveform as well. So on the right hand side we can change the phase displacement. So now we only have watts, we have no reactive power, but we can change that. You can see if once we start changing that, the voltage and the current are not in phase anymore. And now you start to get negative power as well. While in the previous case you only had positive power. Now that should tell you something. What is now positive, what is negative power? We're going to look at that in detail now. But this is what you're going to use for your practical. And there it's now 90 degrees. And now we only have, the total watts is now negative. It's not positive anymore because of the reactive power component. So we have three distinct types of power. So we have what we call apparent power. That's the power seeming to be transmitted as the product of the RMS, current and voltage. Then we have the active power. That's the true net rate of energy transfer, which is measured in joules per second or watting. And then we have the VAR, the reactive power. So that's the rate of transfer of energy that does not go anywhere but reciprocates between the source and the load, and it's measured in VAR for the R for the reactive component. So that's what you've seen over here. So that's the VAR component. So you can go and play around, and you have to play around to do the practical so you can see how it changes. Now the reactive component, this is a good example of what it actually is. So if you buy a beer, then what you're interested in is the liquid, but you end up with quite a lot of foam, which you don't really want and you don't want to pay for that, but you end up with that. So that's the same with reactive power. And from the municipality side, they charge you for the full apparent power, not just the active power that you use. So you want to get this foam as small as possible. That's why they put in some active power or power factor correction capacitors or any mechanism that can reduce the amount of foam. Otherwise you'll in any case have to pay for the foam. Welcome Felix. As I said, by past, we might have 10 people. Now we have the power triangle, because we said that we have apparent power, active, and then the reactive component. So there's the apparent power S, we have the reactive component and the active component. So that shouldn't be S, that should have been Q for the reactive component. Power factor is P over S. And the angle is A cos power factor. So the two components, the cos and the sinus of your angle, power factor angle, and that gives us the power triangle. So apparent power, V times I, active, cos theta, sin theta, and cos theta is known as the power factor, and then the angle as the power factor angle. And that angle depends on the ratio of the resistance to the reactance in the circuit. So if it's pure resistance, then that component is 0. So our three-phase system loads can be in delta or star connection. So you can see why this is called delta, and this has got a star point. So we can have a star connected supply, maybe from the transformer, but the load can also be connected in a star configuration, as you see over here. Now, power in three-phase circuit is the sum of the power in the individual loads. So when the loads have equal resistance in all phases and equal reactance in all phases, then the load is then said to be balanced. Now the current drawn will have the same power factor in each phase. So it will just be 3 times the voltage times the current times the power factor. So V and I being the voltage and current in each phase, and it will depend on the connection of the load, if it's star or delta. Why? Because in the star connected circuit, the line voltage is equal to the phase voltage times the square root of 3. So there I've indicated to you, so you can see the phase voltage is smaller compared to the line voltage. So that's why the line voltage is square root of 3 of the phase voltage. If you look in a delta connected circuit, then you can see the current. The line current is higher than the phase current because it's a combination of 2 of the phases. So that's why it's equal to the square root of 3 of the phase current. But now line and phase voltage are exactly the same. So here in the star connection, you can see the phase current is equal to the line current. But the phase voltage, which is only one phase, is not equal to the line voltage, which actually covers 2 phases. So that's why we have the square root of 3. Now looking at the delta configuration, you can see the phase current is smaller than the line current because that line current consists of 2 currents, 2 phase currents combined to give us the line current. The phase voltage, however, is the same as the line voltage. So there when we measure the phase voltage is exactly the same. This is also the line voltage. Now to get the value of your power independent of the connection, that's then the square root of 3 times the line voltage and the line current. So the line voltage and line current depends on if we have a delta or a star connection. So just if you remember the difference, then you would know to use the right values. Here's an example: 3-phase load connected to a 400 volt circuit draws a line current of 10 amps at a power factor of 0.6. Now what is the apparent power, the watt and the reactive component? So we've already seen these 3 formulas. S is VI times square root of 3, and the rest we have the cos theta and sin theta. Now this is one way of calculating it. The other way is because they told us that cos theta is then equal to 0.6. We just take minus 1 of that, will then give us the angle. And then we can just replace the angle, and then that will give us sin theta, which is 0.8. So once we have that, we can calculate the apparent power, the active and the reactive component. And there is the 3 components. So in this circuit, the active energy consumed in 1 hour will be 4.127 kilowatt hours or 4.127 units. So that's just an example applying the formula. Now if you compare 3-phase versus single phase, so in a 3-phase transmission line we'll have less conductor material than in the single phase line, for transmitting the same amount of power. For a given frame size, three-phase machine gives a higher output than a single-phase machine, and it also takes more load than a single-phase machine. Also, three-phase motors, they are self-starting, they are more efficient, and on the other hand, single-phase motors are not self-starting, less efficient. Three-phase power is typically 150% more efficient than single-phase in the same power range. So that's why we have our three-phase systems.